The Stern-Geary equation is very useful in corrosion because it allows us to calculate the corrosion current density as the ratio of B, which is the Stern-Geary coefficient, to Rp, which is the polarization resistance, and can be measured non-destructively on a corroding surface. B in this expression is the Stern-Geary coefficient, given by this equation. Here, Ba and Bc are the anodic and cathodic Tafel coefficients, respectively. So, let's explore where this expression comes from and how we can use it to estimate the corrosion rate non-destructively. First of all, the Stern-Geary equation is derived mathematically for a specific case of corrosion. Strictly speaking, the Stern-Geary equation provides an accurate estimate of the corrosion current only in situations where both the anodic and cathodic reactions are under activation control. This means that the value of the anodic current increases exponentially as the potential increases, and the value of the cathodic current increases exponentially as the potential decreases. Generally, the behavior of a corroding system in terms of current response to a variation in potential can be represented by a curve, like this gray curve, which is the difference between the anodic and the cathodic current on the metal surface. If we want to write the equation representing this curve, we can write that the current density I, which can be physically measured and is represented by the gray curve, equals the corrosion current density that multiplies a term accounting for the anodic current, generating this red curve, minus a term accounting for the cathodic current, generating this blue curve. Again, the curve that can be measured is the difference between the anodic and the cathodic current on the surface, and is represented by this gray curve. In order to derive the Stern-Geary equation, we need to differentiate the gray curve and consider the value of its derivative near the corrosion potential. So in order to differentiate the gray curve, which is represented by this equation, we need to remember that the derivative of E raised to a function of eta with respect to the overpotential eta equals the derivative of the function multiplied by E raised to the function. Also, the derivative of k multiplied by eta with respect to the overpotential eta equals k. For the anodic term, which is this first term here, we have that the derivative equals 2.3 divided by Ba multiplied by E raised to 2.3 divided by Ba multiplied by eta. And similarly, for the cathodic term, the derivative with respect to the overpotential equals 2.3 divided by Bc multiplied by E raised to minus 2.3 divided by Bc multiplied by eta. So if we combine the derivatives of each individual term, we obtain an equation for the derivative with respect to the overpotential eta equals the corrosion current density multiplied by this expression that contains the anodic and cathodic Tafel coefficients and the value of overpotential. When we are at the corrosion potential, the overpotential eta equals 0. Thus, both terms here equal 1. Therefore, the derivative of this equation that represents the measured current at the corrosion potential, where the anodic and cathodic reactions have the same value, can be written as 2.3 multiplied by the corrosion current density, multiplied by the sum of 1 over Ba plus 1 over Bc. Now, we need to focus very near the corrosion potential, as it is possible experimentally to acquire the gray curve over any range of potential. However, doing so only very near the corrosion potential ensures that the measurement is non-destructive. We know that the slope of this curve provides the reciprocal of the polarization resistance because effectively the measurable curve is in a plane of current versus potential, where resistance is the ratio between potential and current. Since the polarization resistance is effectively the reciprocal of this derivative that we just calculated, we can write that the polarization resistance equals 1 divided by 2.3 multiplied by the corrosion current density multiplied by the sum of 1 over Ba and 1 over Bc. This allows us to write this expression where we have that the corrosion current equals 1 divided by Rp multiplied by 2.3 multiplied by 1 over Ba plus 1 over Bc. Thus, we can define the Stern-Geary coefficient as 1 over 2.3 multiplied by 1 over Ba plus 1 over Bc. Combining the fractions and rearranging, we obtain this more common form where B equals Ba multiplied by Bc divided by 2.3 that multiplies Ba plus Bc. So now we understand where the expression of the Stern-Geary equation comes from, as we have that the corrosion current in this equation equals B, that we have calculated as above, divided by the value of the polarization resistance, which we can measure experimentally by sweeping the potential and measuring the current very near the corrosion potential. The final step is to understand how to obtain BA and BC for use in the Stern-Geary coefficient. We can obtain their values by performing a large-scale potentiodynamic polarization on a specimen that is undergoing corrosion in the same environment as the specimen we want to study non-destructively, plotting the response on a semi-logarithmic scale. Here, the vertical axis represents the potential and the horizontal axis the current, plotted on a logarithmic scale. The slope of these lines, assuming that both reactions are controlled by electron transfer in volts per decade, provides the values of BA and BC, which can be used in this equation to obtain the Stern-Geary coefficient. Once we have the Stern-Geary coefficient, we can use it in this equation to obtain the value of corrosion current. Once we have measured, non-destructively, the value of polarization resistance on a specimen of interest. If you are interested in learning more about corrosion, we have many courses at Corozone, tailored for engineers, researchers, and students, covering a wide range of topics. Please visit corozone.com to find the corrosion course that is right for you.